go ahead and get started. A couple of things I want to discuss with you guys. First thing is this. When is your final exam in this class? Thursday, May 2nd. What time is your final exam? 3 o'clock. You got to be there about 2:30. Here's the big one. Where is your final exam at? CHHS room 155. That's where we're having our big final exam at and stuff. So I put down all this information for you guys down here to let you guys know our final exam is May 2nd, 3 o'clock at CHHS 255. You need to show up just after 2:30 so you can fill out a bunch of forms and stuff. So plan on being there around 2:30, 2:35, 2:40, something like that. You need a number 2 pencil, your student ID, your TI-83 or 84 calculator. Once the exam starts, right at 3 o'clock, no one will be allowed in the exam. It's like the SAT thing. You open the test booklet and start taking it type thing here. So I also have put a bunch of old final exams here, and here's a blank copy of the final exam and a video solution of me going through the entire final exam. And I've put spring 2017, fall 2016, spring 2016, fall 2015. I put up quite a few of them up here for you guys. And I'm telling you, you need to study these things because the exam is a different format. I also put up here a couple of, as I promised, web work problems that we're not doing in class. I've got you covered, but I made some videos for you guys that I actually cover this stuff. And on this one, I actually went through and looked at some final exams and pulled out some of the questions from chapter 8, test 4 for you guys and stuff. So that's definitely worth looking at and taking a look at. The other thing I want you to tell you guys about also is don't forget to fill out the course evaluations for this course. As you may or may not know, the university and the IT department has decided that the Panopto videos are not well worth the money that they're spending for them, and they're going to be turning these things off. I disagree with them wholeheartedly in the feedback that I get from students, but they just don't tend to agree and see my way in terms of, because they don't actually know all the different things that we do with all the videos, especially when you teach the large classes. I think the videos are actually very advantageous, and they're bringing up another system that I can continue to use this stuff on, but it's nowhere close to the same system that we're working. And the most important aspect for me is 2 things. Number 1, I can edit the videos, and then the other thing that I can do, so I can make snippet videos and shorten them up instead of making all new videos. And the other thing is that I can share it with students. So, you guys that are taking linear algebra, quite a few of you guys have come to me and asked me, hey, Dr. Taylor, you got any of those videos from when you taught linear algebra? Yeah, I do. And I can open them up for you guys and I can share them so you get another different perspective of the material when you're doing that stuff. I mean, we're in the 21st century, but I'm fighting an uphill battle, and they've already said no and turned it off. But if you don't mind, please fill out the course evaluations and on the course in general, what you thought about it, and also let them know, because this is the only feedback the IT or any of the administration actually hears from you guys, is when you actually fill out the course evaluation stuff. Tell them what you think about the videos. If you think they're worth it, great. If you don't think they're worth it, let me know about it. Is there ways we can improve this stuff? Let us know about it. That's what we want to know. And let us know how we're doing and stuff. So, again, here's your test review. This will be due on Friday at the review session. All right. So let's go ahead and get started. We are now in the big last section of Calculus 2, Test 4, Chapter 8 material. All my numbers running together here. This is Chapter 8.7, Taylor Series. Now, as you walk through these things, and hopefully you'll watch the awesome pre-section video on this stuff, you've seen basically the idea behind this. But let me explain it very simply. This is real important material. Very important material. Here's the deal. Taylor, that was my great-great-granddaddy. He discovered this stuff back in the 17th century the relationship between the derivatives of a function and the actual function itself. And this is what we use in the wonderful world of computer science, which kind of reaches into all the things that we do today, and especially my engineers and electrical engineers in particular, but my mechanical and civil. This is stuff you guys need to know. You're going to see this stuff again. And this is called a Taylor series. Taylor discovered the relationship between a function and a particular centering point of that function and how it relates to all the derivatives. Now, in Calculus 1, you did something called linearization. Basically, you found the equation of the tangent line. You needed a point and the slope. The derivative was the slope of the tangent line. Times x minus a was your point, and f of a was your y-coordinate. This is the equation of the tangent line. But that's 1. But if you look at it divided by this 1 factorial, when you look at the second derivative, this gives you your concavity aspect. Second derivative evaluated a times x minus a squared over 2 factorial. And Taylor discovered if you keep going on and make an infinite series, this third derivative evaluated a times x minus a cubed divided by 3 factorial plus dot dot. This gives you an infinite series. But this infinite series is actually equal to this particular function. And you look at this and you go, okay, what's the big deal? Well, let me do this first example for you, and then let me show you the big deal of why this is important. So, this is a Taylor series. You've got to have two things. You've got to have a function, and we've got to give you a centering point where you want this Taylor series to be centered at. That's what we call A. A is your centering point. So in this first example, I have here, find the Taylor series representation for the cosine of x centered at the point pi halves. So you've got to have your function, f of x. This is the cosine of x. But you need also a bunch of derivatives. So we need the first derivative. What is the derivative of cosine of x? Negative sine of x. What is your second derivative? Remember, this is calculus 1. Don't integrate it. Take derivative of it. What is the derivative of negative sine of x? Well, derivative sine of x is cosine of x. With the coefficient out front, that makes it negative cosine of x. What is your third derivative? What is the derivative of negative cosine of x? Well, derivative cosine of x is negative sine of x, but negative that makes it back to positive sine of x. What is your fourth derivative? Derivative sine of x is cosine of x. But you're going to evaluate these derivatives at the point A. And if you'll notice, the cosine of pi halves is 0, and never stop on a 0. So keep writing down and taking more derivatives until you don't have a 0 term for your derivative. So your fifth derivative, derivative cosine of x, is back to negative sine of x. And derivative sine of x, sine of x at pi halves is actually 1, so this is not going to be a 0 term. So now we're going to evaluate these guys, f of pi halves. What was the cosine of pi halves again? Things we know from high school, 0. What is negative the sine of pi halves? The derivative at pi halves is negative sine of pi halves. Sine of pi halves is 1. Negative that makes it negative 1. Your second derivative at pi halves, cosine of pi halves is what again? 0. Negative that, still 0. Your third derivative at pi halves, this is the sine of pi halves, which is 1. Your fourth derivative at pi halves, the cosine of pi halves is 0. Never stop on a 0 term, so one more derivative. Your fifth derivative at pi halves, sine of pi halves is 1. Negative that makes it negative 1. These become the part of the coefficient of what we call the Taylor polynomial, your Taylor series. So here's the deal. So I'm trying to, let me blow this back down a little bit so you can see the formula, because this is what's going on. The original function, my original function is cosine of x. The cosine of x actually equals f of a. F of pi halves was 0. Plus f prime of a. F prime of pi halves is negative 1 over 1 factorial, that gives me the coefficient, times x minus a, which is pi halves. Plus your second derivative evaluated at pi halves. That would be 0 over 2 factorial times x minus pi halves squared. And so I'm going to put in each term because I want you to see it. Even the 0 terms, I'm plugging in each one. So plus Your next derivative, which is your third derivative, the third derivative of pi halves was 1 over 3 factorial times x minus pi halves cubed, plus your next derivative, which is 0 over 4 factorial times x minus pi halves to the fourth, plus your fifth derivative, that's where we stopped at, negative 1 over 5 factorial times x minus pi halves to the fifth, but it is an infinite series. So it goes plus dot, 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 and goes on forever. Now let's clean this guy up. So again, I wanted you to see that literally all I did was plug in for my derivatives, their values, plugged in for A, the centering point pi halves, and I've created the Taylor series for the cosine of x. Now, cleaning this guy up. That means the cosine of x is equal to, well, no reason to write 0. This will be negative 1 over 1 factorial times x minus pi halves. 0 divided by 2 factorial is still 0 times x minus pi halves squared. That's 0. No need to write that. Plus 1 over 3 factorial times x minus pi halves cubed. There's another 0 term. Minus 1 over 5 factorial times x minus pi halves to the fifth. And hope from this you can catch a pattern on these guys. So this right here is what the cosine of x is equal to. And you look at this going, well, that's the Taylor series for the cosine of x evaluated at pi halves. Whoop-de-deal. No, it is a big deal, actually. Let me explain. You ever wondered how your calculator actually works? You computer science majors, and especially you computer engineers out there, you should be very excited by this fine fact, because we're discovering you how this stuff actually works. You know, there's a cosine button for you right there. See that old cosine button? And notice, and I'm going to be in radian mode here. Mode, radians, there it is. So, I hit that cosine button, and let's say I take the cosine of 1.5. And the calculator gives me an awesome 0.070737217. How does it do it? What does it do? What does the actual calculator do? A calculator is exactly what Pascal invented back in the 1700s. It's an add, subtract, multiply, and divide machine. All we've done is kind of computer scienced it into doing more things for us. Let me show you. Instead of typing in cosine, let us type in 1.5 into this polynomial here. This will be negative 1 times 1.5 minus pi divided by 2, right? Divided by 1 factorial. 1 factorial is 1. Plus 1 times 1.5 minus pi halves cubed divided by 3 factorial. Let's calculate. 3 factorial is 3 times 2 times 1, which is 6. Minus 1 times 1.5 minus pi halves raised to the 5th power divided by 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1, 120. So instead of plugging in 1.5 here, I plugged it into the polynomial. And I didn't take it out to infinity. I stopped with the 5th degree term. But if I hit enter, what do I get? Oh, the exact same number. The reason why is, look, once you start taking these higher powers, and if you get close to your centering point, these guys become very small fractions. And very small fractions raised to power is basically really smaller fractions. This calculator, you know, this is some kind of irrational decimal. It goes on forever, but not in the calculator. They stop it around the 10th or 11th decimal place. You only see 9 decimal places, but it does remember a couple more after in case you want to calculate something off of it. But it does cut it off. And look, what's the difference between cosine of x and this guy? This is a polynomial. When I plugged in 1.5, then we subtracted off a number, then we divided by a number, then we powered it up, which means multiply, and then we added it to the next term. We're add, subtract, multiplying, dividing it. This is how we get all these really cool buttons like sine, cosine, tangent, e to the x, and all these other wonderful buttons on the calculator. what's been programmed on the calculator is not some computer bank that has all the digits of the cosine memorized. No, it's got the program of the Taylor polynomial into this guy, and instead when you type in cosine, it plugs it into the polynomial that it has memorized and turns it into abstract, multiply, and divide, and crunches out your number. Beautiful computer science is what this really is. And you're going to see this stuff a lot, differential equations, especially when I start picking on my electrical engineers in here that are, especially in circuits. Circuits, you have signals, and signals is nothing based on a bunch of series type of problems. You are not going to see this just this time and be gone with it. Series is going to come back and haunt you a lot. My statistics majors in here, oh yeah, this series stuff is going to be huge in your future. And don't get me started on my computer science majors, because they're the ones that help develop all this stuff so we can actually have really cool computers in our office and cell phones and crap like that. So, very, very important stuff. Does that make sense? Now, what you need to memorize is this. Now, if you look at this Taylor series formula, we wrote it out for you, but you can also write this series formula. It's the sum as n goes from 0 to infinity of the nth derivative evaluated a times x minus a to the n over n factorial. Just to remind you, when you plug in the zero term, n equals 0, the zero derivative is actually the functional value. 0 factorial by definition is actually equal to 1. 1 factorial by definition is 1, because these are counting arguments. So when you have 0 factorial, that actually means you're dividing it by 1. That gives you basically the first term, which makes it just a constant here in terms of your series. So we can write it down as a very nice little formula. And it is an infinite series. So these two guys are actually equal to each other. However, if you're going to actually cut this thing off and you're going to evaluate the function at a particular point, you always need to have that point near your centering point. That actually gives you a very, very good estimate when you start cutting terms off. However, Taylor series, very important, is f of a plus f prime of a times x minus a over 1 factorial plus f double prime of a times x minus a squared over 2 factorial plus f triple prime of a times x minus a cubed over 3 factorial plus dot, dot, dot. A is, and when I give you a Taylor series, I got to give you a function, and I got to give you a centering point. What is the easiest centering point you can think of? What's the easiest number to plug in any kind of function? 0. Well, there was a fellow by the name of Maclaurin, and I pick on him because I say he got a free PhD off of this one. He took this Taylor series, and he said, well, the most easy point to ever plug in on anything is actually 0. And so we have a very special name for a Taylor series centered at 0. It's called a Maclaurin series. So on a test, we're going to, hey, here's a function. Calculate, write out the Maclaurin series for this function. And they're not going to tell you what the centering point is. The reason for that is it's implied. For a Maclaurin series, what's your centering point? 0. So we're going to do one of the most famous Taylor series of all, the famous e to the x. And we'll make it a Maclaurin series. We're going to center it at 0. So first thing you've got to have is a bunch of derivatives. Well, don't hurt yourself. F of x equals e to the x. What's the first derivative of e to the x? E to the x. What's your second derivative of e to the x? Okay. Oh, might as well. What's the third derivative of e to the x? Well, I think I caught the pattern on that. But remember, you're not going to be plugging in functions into this guy. You need a numerical value. You've got to evaluate it. So Maclaurin series, we evaluated at 0. What's e to the 0 equal to? 1. F prime of 0. E to the 0, still equal to 1. F double prime of 0. E to 0, still hasn't changed, it's 1. And f triple prime of 0, e to 0 is 1. So all your derivative terms are going to be 1. So when you write out a Maclaurin series for e to the x, the actual function e to the x is equal to f of 0, which is 1, plus f prime of 0, which is 1, supposed to be times x minus a, but a is 0, so you just get times x over 1 factorial, plus f double prime of 0, e to 0 is still 1, times x squared over 2 factorial, plus f triple prime of 0, which is 1, times x cubed over 3 factorial. I think I called a pattern, plus dot, dot, dot. And the key to this math, honestly, is catch a pattern. So e to the x is actually equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. So if you wanted to write a series for this guy, we're going to start it at n equals 0, so that gives me my constant, to infinity of what seems to be the pattern. It's x to the n power divided by n factorial. This is the Maclaurin series for e to the x. And these two functions are equal to each other. And it's the same idea. Yeah, I got a great old cool e to the x button on this calculator. So when I do e to the, I don't know, 0.25, and I get some kind of number, 1.2840, whatever here, how does the calculator do it? Does it have e, 2.71828, that irrational number stored in its computer banks? There are no computer banks, dudes. It's just a calculator, but you've got this little program set for it. And what's set for this guy is actually the Maclaurin series. Does that make sense? So you put 0.25 in for all the x's up to a certain number, and then it cuts it off because we're within the tolerance, and it chunks out what the answer is. It adds, subtracts, multiplies, and divides. Now, here's the big deal. This is why Maclaurin and Taylor series is so important. Listen to my words and believe me, because I'm being honest with you. Taylor series are easy to manipulate. We love power series. From a programming perspective, they're easy to manipulate. Let me show you. All right, find the Maclaurin series representation for g of x equals x times e to the x. If you can come up with a power series for just part of the problem, you can extend that to the entire problem. This is a trivial problem. Let me show you. G of x is equal to x times e to the x. I have a Maclaurin series for e to the x. I just derived him. So this is going to be x times the Maclaurin series for e to the x, which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. How would you clean that up? I would distribute. Does that make sense? And when I distribute, I get x plus x squared over 1 factorial plus x cubed over 2 factorial plus x to the 4th over 3 factorial plus dot dot dot. And if you wanted to write the series formula for this, this would be x times the Maclaurin series formula for e to the x is the sum as n goes from 0 to infinity of x to the n over n factorial. And put your two x's together. When you multiply, you add exponents, and you come up with a formula. The sum is n goes from 0 to infinity of x to the n plus 1 over n factorial. Does that make sense? If you can come up with a series for part of your problem, you can come up with the actual series for the whole thing. Does that make sense? All right. Now, if you go back, and I skipped over this web work problem because I actually made a video for you guys so you guys can go over some of the homework problems at your leisure. But this was one of our homework problems right here. This was, we wanted to evaluate the integral of 2x minus the tangent inverse of 2x divided by x cubed. It was from the last section here. Again, I'm telling you about the idea that series are easy to manipulate. If you go back and remember, we had a series representation for the tangent inverse of x. It was this. It was x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9 minus dot dot dot. This was the series that we developed from the power series representation stuff we did. We took the derivative of this guy, turned it into a over 1 minus r, integrated it, and came up with this series for it. But this is, if you actually look at this thing, is actually also known as the Maclaurin series for the tangent inverse of x. If you turn the page, you will see the actual series that we really do expect you guys to have memorized. The 1 divided by 1 minus x, that's the sum as n goes from 0 to infinity of x to the n, x plus 1 plus x squared plus x cubed dot dot dot. The e to the x one we just derived ourselves, which is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. The sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And the tangent inverse is the one we just wrote down, which we derived actually last time, which is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, dot, dot, dot. Because here's the deal. Now you can, if I give you some bizarre function, you can actually go through and take the derivatives of it like we just did and plug it in. But what we're going to be doing is manipulating these guys and showing you the power of these Taylor/Maclaurin series. Okay? So, and that's what this whole section is going to be about. We're going to be deriving these particular guys. So, but instead of taking the derivative of these guys, these are the core. So if I have these memorized, then all I got to do is basically manipulate what I have memorized. And it's so much easier. E to the x, pure memorization. 1 over 1 minus x, pure memorization. And where people get confused and in trouble is the sine, cosine, and tangent. Have you ever noticed, if you analyze a sine function, it's an odd function. It's symmetric with respect to the origin. And because it's odd, centering at 0, Maclaurin series, you just get the odd powers. X minus x cubed over 3 plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Does that make sense? It's just the odd powers. Cosine is an even function. It's symmetric with respect to the y-axis. So you get nothing but the even numbers. Remember, 0 power is considered even. So you get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. They alternate. Sine is odd, cosine is even, and you got the 1 with it because that's the 0 is even. So when you understand that, they become a little easier to manipulate. And you look at tangent inverse. How am I going to memorize that? Look at the difference between the tangent inverse of x and the sine of x. It's the same series except for one thing. What's missing? They're both odd, but what's missing is the factorials on the bottom. Does that make sense? So if you got sine memorized, you got tangent inverse memorized. Just drop the factorial. And these are then the goal is to manipulate these guys. So, and that's actually what we did. When you watch the video on this guy, we built this guy because, listen up, power series are easy to manipulate. So here's the deal. I got tangent inverse of 2x. Well, I got the power series for tangent inverse of x. So how do I come up with a power series for the tangent inverse of 2x? Classic computer science. What are we mathematically doing? Instead of x, what do I got? 2x. All you got to do is replace x with 2x. And you can write it down. This will become 2x minus 2x cubed over 3 plus 2x to the 5th over 5 minus 2x to the 7th over 7 plus dot, dot, dot. You can clean that up, of course, but then you got your power series for this guy. And then you can take that series and plug it in here and subtract 2 and distribute negative and divide by x cubed and come up with a power series for this guy. And then you can integrate that darn power series and you can do all kinds of good stuff to it. Does that make sense? So I did this problem on the other class and the video that I created for you guys. But this is the idea of why we love power series. They're easy to manipulate. So look at this problem right here. So let's do a problem you haven't done yet, or at least analyzed on a video that I made. Here it is. Find the Maclaurin series representation for h of x, which equals x times the cosine of 2x. What you're going to do is you're going to build these guys based on what you know and have memorized. Because you don't want to sit there and have to take the derivative of this thing 15 times, because this is going to be really painful. Product rule with some chain rule action. I mean, don't get me wrong, you can do it if you want to go old school and actually use the formula. But the point is, once you got one series, you can start expanding it. So, I have the Maclaurin series for the cosine of 2x. Excuse me, cosine of x. We'll start with that guy. Cosine of x. I'm going to build the cosine of 2x. The cosine of x is right up here. Cosine is even. So it is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. And key to math is catch a pattern. Hey, let's just do one more term to see if you're catching a pattern. what would the next term be? They alternate, so it'll be a plus x to the what? 8 over 8 factorial. And then you can go on forever with that stuff. But that's not the series we want. What do we want? We want the cosine of 2x. So guess what I'm going to do? Replace all the x's with 2x. This would be 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus 2x to the 8th over 8 factorial plus dot, dot, dot. Does that make sense? But then you want to clean it up. Cleaning it up, I'm going to distribute my powers. This will be 1 minus 2 squared is 4, x squared over 2 factorial, plus 2 to the 4th is 16. So that would be 16x to the 4th over 4 factorial, minus 2 to the 6th power is 64, minus 64x to the 6th over 6 factorial, plus 2 to the 8th power is 256, x to the 8th over 8 factorial, plus dot, dot, dot. And just plus dot, dot, dot to keep on going. But they alternate. But that's not what we're supposed to build, but we're building it piece by piece. Now that I have the Maclaurin series for the cosine of 2x, I want h of x. H of x is equal to x times the cosine of 2x. That would be x times this series. 1 minus 4x squared over 2 factorial plus 16x to the 4th over 4 factorial minus 64x to the 6th over 6 factorial plus 256x to the 8th over 8 factorial plus dot, dot, dot. And I want to clean it up. So what's the last move I'm going to make with this stuff? I'm going to distribute. Distributing my x through all the terms gives me x minus 4x cubed over 2 factorial plus 16x to the 5th over 4 factorial minus 64x to the 7th over 6 factorial plus 256x to the 9th over 8 factorial plus dot, dot, dot. That is what x times the cosine of 2x is. So if I actually type in, a number in for x, like, 1 times the cosine of 2 times 1, and actually calculate what the calculator gives me, and plug in 1 into this guy here, I'm going to get the same thing. After a while, I cut it off, but decimally speaking, it's the same thing, because this is what the computers are doing today. It's what our calculators do. Does that make sense? Did I lose you guys anywhere? Okay. Now, you'll see on some web work problems we're going to get to of how to manipulate these guys. But the last form you guys need to know is going to be what we call the binomial series. Okay? Binomial series. You should have been familiar with this way back in high school, and I'll kind of connect you together with this stuff. But the first thing you need to know is combinatorics. Branches off into a completely different branch of mathematics, probability theory and statistics. Combinations. A choose B is how you would read this. And what we're really asking you is this. When we do A choose B, you've got A items, and you want to pick B out of them. And that's a formula. This is where your factorials, that counting argument comes in at. A choose B is going to be A factorial divided by A minus B factorial times B factorial. And what this is telling me, and I'll give you an example right here. I got 7 items, and I want to pick 3 of them. How many different ways can I pick 3 items? And this is with out order. Order doesn't matter. So I can pick the first 3, the last 3, and how I pick each individual one doesn't matter. But I got 7 items, and I got to pick 3 of them. How many different ways could I pick 3 items out of 7? So let's find out. Let's count it up. A is 7, B is 3, so this would be 7 factorial divided by 7 minus 3 factorial times 3 factorial. That is 7 factorial divided by 7 minus 3 is 4 factorial times 3 factorial. When we did the ratio test, we always used ratio test on powers of n and factorials because the powers of n in factorials always cancel. So I'm not going to go to grab my handy dandy calculator yet. I'm going to show you how to do this without a calculator. What is the definition of 7 factorial? It is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 factorial, which is 4 times 3 times 2 times 1 times 3 factorial, which is 3 times 2 times 1. And what do you see? Well, the 4, 3, 2, 1 cancel with the 4, 3, 2, 1. What is 2 times 3? 6 cancels with that 6. And I'm left with what? Oh, it's going to cancel with the 6 there. I can't grab the wrong guy. Cancel with the 6. So I'm left with 7 times 5 divided by 1. Does that make sense? The 7's left there, the 5's left there, but everybody else cancels. 7 times 5 divided by 1, which is 35. We have a button on the calculator that does this. I'll show you where it is if you plan on taking probability and statistics sometime. If you go to math and scroll over to probability, there's a button called NCR. Combinations is what the C stands for. N, choose, R. So you first start with your top number, 7. You go to math, probability, NCR, and pick 3. 7, choose 3. How many ways? Yep, 35 ways. Okay? But what this is doing is counting the number of ways you can do something or other. And you go, why is this important? Well, because of the binomial series. Here is my binomial series. I've got 1 plus x to the k. That is equal to, if you expand it out. Now, in the old days, aka high school and junior high school, we would have something like 1 plus x cubed. What 1 plus x cubed meant was 1 plus x times 1 plus x times 1 plus x. And if you wanted to know what that was, you fold it out like 3 different times and then be able to get your answer and expand it out. This is a fast way of doing that. It's called the binomial series, a fast way of expanding. What it's going to end up being is this. It's 1 plus x to the k. That's equal to 1 plus k times x plus k times k minus 1 over 2 factorial x squared. K times k minus 1 times k minus 2 divided by 3 factorial x cubed plus, and it goes on forever. And if you write this as a formula, this k times k minus 1 divided by 2 factorial stuff is actually your k choose n. It's your combinations from this formula up here. K choose n times x to the n. So this gives you a series and a fast way of expanding it. Just a little side note, and we talked about this before, 0 factorial by definition is 1, and 1 factorial is equal to 1. So if I have k choose 0, you got k items. Pick none of them. How many which days can you do that? There's only one way. Don't pick anybody. But you can calculate it. K factorial divided by 0 factorial times k factorial. And 0 factorial is 1, so k factorial divided by k factorial cancels, you're left with 1. If you've got k items, and you pick k of them, there's only one way to do that. Grab them all. K factorial divided by k factorial times k minus k, which is 0 factorial. That also gives you 1. This counts the number of ways you can take k items and pick n out of them. So just to show you, here's this problem here. 1 plus x to the 5th power. Okay? I want to use the binomial formula to expand this. Because in the old days, aka high school, I would do 1 plus x times 1 plus x times 1 plus x 5 times, and then I would have a field day at folding it out. I'd come back about 20, 30 minutes later, see how my high school kids are doing, and see how many 14 different answers that I got in the classroom. Okay? Well, there's a faster way of doing this. It's called the binomial series. So, here in this problem, all you really need to do is analyze k. K is equal to 5, right? And I have the formula memorized. 1 plus x to the k is equal to, catch a pattern, 1 plus kx plus k times k minus 1 over 2 factorial, x times x squared, plus k times k minus 1 times k minus 2 over 3 factorial, x cubed plus dot, dot, dot. There's a pattern here. What we're teaching you guys, just like with your Taylor and Maclaurin series, is the pattern. K is 5. So 1 plus x to the 5th would be equal to 1 plus k is 5. That'll be 5 times x plus k, which is 5 times 5 minus 1, which is 4, divided by 2 factorial times x squared, plus 5 times 4 times k minus 2, which is 3, over 3 factorial x cubed, plus 5 times 4 times 3 times 2 over 4 factorial times x to the 4th, plus, catch a pattern, 5 times 4 times 3 times 2 times 1 over 5 factorial times x to the 5th, plus, your next one would have been 5 times 4 times 3 times 2 times 1. What comes below 1? Times 0 over 6 factorial times x to the 6th. But once a 0 shows up, what happens to my entire series? It goes to 0, so it actually stops. This is an infinite series, but every term after 5 has a 0 in it, which completely kills it off. Does that make sense? So now, clean it up. This would be 1 plus 5x plus 5 times 4 is 20. 22 factorial is 2. 20 divided by 2 is 10, x squared. Plus 5 times 4 is 20. Times 3 is 60. 60 divided by 3 factorial, which is 3 times 2 times 1, which is 6. 60 divided by 6 is 10, x cubed. Plus 5 times 4 times 3 times 2. Divided by 4 factorial. 4 factorial is 4 times 3 times 2 times 1. The 4 3 2's and the 4 3 2's cancel. She left with 5 over 1, which is 5, x to the 4th. And 5 factorial is 5 times 4 times 3 times 2 times 1, which cancels with the 5, 4, 3, 2, 1. You get plus x to the 5th. So, if I take 1 plus x to the 5th and FOIL it out 5 times, I get 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the 4th plus x to the 5th. It's a fast way of FOILing it out. Does that make sense? But it's more important than just fast way of FOILing it out. But in this example, that's what it does. So turn it over. What about this guy here? Well, this one, I'll have to admit to you, I would probably FOIL it out in my head faster. I can do the binomial series on it. But the binomial series, just to remind ourselves, is 1 plus x to the k. That's equal to 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 over 3 factorial x cubed plus dot dot dot. Just memorizing the pattern. Here, k is equal to 2. So if k equals 2, now honestly, if I FOIL this out, I can do this in my head. What's 1 plus x times 1 plus x? That is 1 plus 2x plus x squared. I could do that one because I've done it 10,000 times before this. But if I did k equals 2, here it goes. That'll be 1 plus 2x plus 2 times 2 minus 1, which is 1, over 2 factorial times x squared, plus 2 times 2 minus 1, which is 1, times 2 minus 2, which is 0, over 3 factorial x cubed. And once you get the 0 in there, this term completely goes away, and you're left with this guy, which happens to be 1 plus 2x. 2 times 1 is 2. 2 factorial is 2 times 1. They cancel, plus x squared. Yep, I get the same thing. I didn't say it was always faster. K is small. Yeah, I could FOIL it out a lot faster than using the binomial series. But when k is large, this is going to be helpful. And when k is a fraction, this is going to be a paramount. So, take a look at this guy here. What about 1 plus x to the 4th? All right. Here, k equals 4. And I have my formula written out right up here. So I always have my formula nearby, so all I got to do is plug and chug. So this is equal to 1 plus 4x plus 4 times 4 minus 1 is 3 over 2 factorial x squared plus 4 times 3 times 2 over 3 factorial x cubed plus 4 times 3 times 2 times 1 over 4 factorial x to the 4th plus 4 times 3 times 2 times 1 times 0 over 5 factorial x to the 5th. And once the 0 shows up, all the terms behind it cancels out. So, expanding this guy out, this is 1 plus 4x plus 4 times 3 is 12. 2 factorial is 2. 12 divided by 2 is 6, x squared. 4 times 3 is 12 times 2 is 24. 3 factorial is 6. 24 divided by 6 is 4, x cubed. Plus 4, 3, 2, 1. 4 factorial is 4 times 3 times 2 times 1, so they completely cancel, plus x to the 4th. There is it expanded out. So it's not that hard, as long as you got the binomial series formula memorized. Put it with, like I warned you guys, chapter 8 in general is huge memorization. Lots and then knowing how to apply it. But I bet you guys had high school, and in high school, they did something called Pascal's triangle. You remember Pascal's triangle? It was basically the fancy way of how to get the coefficients without using the binomial series. You start with a 1 here, and you always put 1s on the outside edge of your pyramid. Outside edge of your pyramid, put a bunch of 1s. And to get the coefficients to go into your expanded binomial, it's this. Any kind of block, internal block, you add the 2 blocks above it that attach to it. So this block's connected to a 1 and 1, that's a 2. This one's connected to a 1 and 2, that's a 3, and a 2 and a 1, that makes that one a 3. This block's connected to 1 and 3, which is a 4. This block's connected to a 3 and a 3, which makes it 6. This one's a 3 and a 1, makes it 4. Go down here, this is a 1 and a 4, makes it a 5. A 4 and a 6 makes it a 10. A 4 and a 6 makes it a 10. A 4 and a 1 makes it a 5. This one's 1 and a 6, 6, 15, 20, 15, 6, 7, 21, 35, 35, 21, 7, and I can go on forever. But what this really is this is k equals 0. You get just 1, 1. K is 1, you get the 2 terms back again. K is 2, 1, 2, 1. When k was 2 up here, notice your coefficients. It's 1, 2x, 1 plus 2x plus x squared. 1, 2, 1. When k was 4, look at your numbers. 1, 4, 6, 4, 1. 1 plus 4x plus 6x squared plus 4x cubed plus 1x to the 4th. This was Pascal's triangle. Pascal discovered the pattern on these guys with his pyramid. But what about this guy? Applying Pascal's triangle on this guy, this would be 1 plus 7x plus 21x squared plus 35x cubed plus 35x to the 4th plus 21x to the 5th plus 7x to the 6th plus x to the 7th. These are your coefficients. That's what Pascal discovered. But if I went and used with k equals 7 with my binomial series formula, I would have gotten the exact same answer. Okay? But why is this so important? All we're doing is following it out. I don't actually have to memorize this formula for that. Wait, we're going to mess you up with something. Okay? Try this guy here. I've got 1 over 1 plus x cubed. Okay? Rewriting this guy, this will be 1 plus x raised to the negative 3. There was no restriction on what k had to be. It's nice if k is a nice positive integer, then they actually terminate and you actually get a bunch of zeros. But once you get fractions or negative exponents, they become infinite series. So, again, writing down my formula, 1 plus x to the k, that's equal to 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 over 3 factorial x cubed plus dot dot dot. That's what I have memorized. In this problem, k is equal to negative 3. And this is going to give you an infinite series, but you can catch a pattern off of it. Here we go. This will be 1 plus negative 3 times x, k is negative 3, plus negative 3 times, negative 3 minus 1 is negative 4 over 2 factorial x squared, plus negative 3 times negative 4 times 1 more negative 5 over 3 factorial x cubed. Now, I didn't write the formula for the next guy. Can you catch the pattern on it? It's going to be negative 3 times negative 4 times negative 5 times negative 6 over 4 factorial times x to the 4th plus, and it really will go on to infinity because you've gotten a bunch of negatives you're not going to catch to 0 anymore. Does that make sense? Now you can clean this guy up. This would be this 1 over 1 plus x cubed as a power series is going to be 1 minus 3x. Negative times negative is going to be a positive. What do we got here? We've got 12 I can do this in my head. 12 divided by 2 factorial is 2. 12 divided by 2 is 6. That gives me 6x squared. Okay. Next one's going to be negative 3 times negative 4 times negative 5. That's back to being negative. That's 60 divided by 3 factorial, which is 6. 60 divided by 6 is 10. That'll be minus 10x cubed. And the next one, and I'm just going to actually put this on the calculator for you guys, negative 3 times negative 4 times negative 5 times negative 6 is 360 divided by 4 factorial. 4 times 3 times 2 times 1, that's 24. Gives me 15. That becomes plus 15x to the 4th plus dot, dot, dot. And it's an infinite series. And look at this guy here. I got 2 divided by square root of 1 minus x. Now they're going to start playing games with you guys. We're trying to turn this into basically 1 plus x to the k. Well, first, I don't do square roots. What's the square root? Half a power. So this would be 2 times 1 minus x to the negative 1/2 power. Half square root on the bottom, half power on the bottom, bring them to the top. But I want this to be a plus. So this would be 2 times 1 plus negative x to the negative 1/2. This 2 is going to stay out front, but in my formulas, what I'm going to do, again, we love power series because they're easy to manipulate. We're going to replace x in my formula with negative x, and k is equal to a negative 1/2. Does that make sense? And so you're going to end up getting, when you write into our series formula, 1 plus kx plus k times k minus 1 over 2 factorial x squared plus dot, dot, dot. You're going to end up getting this. 1 plus k is negative 1/2. But you replace x with what? Negative x times a negative x. Plus k, which is negative 1/2, to minus 1 would be minus times negative 3/2 over 2 factorial times negative x squared. The next one's going to be plus negative 1/2 times negative 3/2 minus another one would be minus negative 5/2 minus 5/2 divided by 3 factorial times negative x cubed plus dot, dot, dot. And then you got to clean them up and distribute your 2. Does that make sense? So this gives you 2 times 1 plus, this would be 1/2 x. A negative times a negative is a positive. This is going to be 3/4 divided by 2 factorial, which is 2, which makes it 3/8. That'll be plus 3/8. Negative squared is positive, x squared. The next one is going to be, yep, that's going to get kind of big on my fractions here. Parentheses, negative 1/2 times negative 3/2 times negative 5/2 divided by 3 factorial, which is 6. And I get negative 0.3125, which makes it a fraction here of negative 5/16. But wait a minute. What is negative 1 cubed? Negative times that negative makes it a positive 5/16 x cubed plus dot, dot, dot. And to finish up your power series, you're going to have to, that 2 is a coefficient out front, distribute that. You get 2 plus 2 times 1/2 is 1x plus 3/4 x squared plus 5/8 x cubed plus dot, dot, dot. And traditionally on web work, they're going to ask you to write in 3 or 4 non-zero terms. This one is, if there's my 4 non-zero terms. Does that make sense? Then I would type this in on web work. We got a few more to do, and I'll do those next time because we're going to really get into the web work from section 8.7 and talk about the kind of problems we like to give you guys on the final exam. So we'll do that next time. See you guys then.